It's about time you answered.
Wait, have you called me before?
No.
Oh, I was about to call you.
Oh, okay. So your video's still not working?
I've been clicking it and it says it's on,
Uh huh.
but then it doesn't load my face.
Oh, okay. Hmm. That's weird. Okay. Let's see. I can get our other Skyper in. Let's see. How do I do that? Oh, okay. Here we go. Um, Janae, are you with us? Janae, can you hear me? Ashley, can you still hear me?
Yeah, I can hear you.
Okay. Not sure what's going on. Hmm. Okay. Oh, I might have a message here.
Yeah, it looks like I.
Um, okay. Oh, okay. All right, so everybody can hear me. That's good. Okay. Um, let's see. All right, I guess I'm ready to get started. Hold on, something's wrong. Dang it. Okay, we're good to go. Um, okay. Now, to pick up where I left off last time with the singular value decomposition. Um, so, a quick recap of what that is. I proved its existence last time. So A, which is m by n matrix. Any m by n matrix has a singular value decomposition, also known as the SVD that my advisor came up with the first algorithm for computing. So U is m by m, and V is n by n. So U and V are both square matrices. And sigma in the middle is m by n, so it's the same size as A. U and V are both orthogonal matrices. So in other words, U transpose U is identity, that's m by m. V transpose V is also identity, that's n by n. Sigma is a diagonal matrix. Sigma 1, sigma 2, so these are sigmas, lowercase sigmas. And all other entries are 0. Sigma 1 greater or equal to sigma 2, and so on. So, and all these singular values are real numbers, even if the matrix A is complex. They're non-negative. These are the singular values. Okay. Now, and then one important connection. I'm going to mention certain properties of the SVD. One that's particularly interesting is that the largest singular value, sigma 1, is actually equal to the matrix 2 norm of A. Okay. Now, so one application that I did mention last time I want to get into today is relates to the columns of U and V, which I mentioned last time are called the singular vectors. Okay. So, oh, actually, before I do that, one other thing I want to mention is about norms. If I take the square root of the sum of squares of all the singular values, then that is actually equal to the Frobenius norm of A. So in fact, you can see right away from this, the Frobenius norm of a matrix is always greater than or equal to its 2 norm. Okay. Now, so next I want to get into the singular vectors. Is there someone able to control the camera down there?
Yes.
Okay. All right. So we're about to switch. Okay. So the if I describe matrices U and V as column partitions, okay, and I'm gonna, as I mentioned last time, R is the number of non-zero singular values, so the number of sigmas that are non-zero, and that is always equal to the rank of A. Okay, and as I mentioned last time, the first R columns of U form an orthonormal basis for the range of A, and then for V, after you leave out the first R columns, the remaining columns form an orthonormal basis for the null space of A. Now, if we keep in mind the properties of a transpose, so if A is equal to U sigma V transpose, then if I take the transpose of both sides, I would get, remember the transpose of a product is product of transposes in reverse order, so that would give me V sigma transpose U transpose. Now, U and V are orthogonal matrices. Their transposes are their inverses. So their transposes are also orthogonal matrices. Sigma is a diagonal matrix. So sigma transpose, also a diagonal matrix. So by transposing everything, I have this SVD of A over here. I have the SVD of A transpose over here. So if I go to these upper columns of U, what subspace of interest do these columns describe? space of A transpose, well, then what's left? Yeah, the range of A transpose. Okay, so range of null spaces above A and A transpose, you can read off the singular value decomposition. Okay. Now, okay. So, now the thing is, if I were to take this product, use sigma B transpose, and describe this using outer products. Some time ago when I first described matrix multiplication, you can view a matrix product into the sum of outer products. I can write this as a sum from 1 up to the minimum of m and n, because those are the only singular values you have. Sigma I, ui, vi transpose. So this matrix product is equivalent to this sum of outer products. But I don't need to let this sum go from 1 all the way up to the minimum of m and n. How many terms do I really need in that sum?
R.
Yes. The number of non-zero singular values. Once I go past r, these terms will be 0. So I can just forget about them. So, so now I have this, sum from 1 to r of sigma I, ui, vi transpose. So what that means is, that leads to what is called the economy size SVD. Where A is, I'm going to write it slightly differently, is U1, sigma 1. Actually, how am I doing the notes? Oh, I did do it that way, except, oh, all right. V1 transpose, where U1 is M by R, sigma 1 is R by R, so square matrix having only the R non-zero singular values along the diagonal. And then V1 transpose would be R by N. So it's still exactly equal to A, you just have only the information you need. So you don't really need to compute the entire SVD if you don't care about any of the information that's related to the transpose, really. Okay. Because you have a range of A, that's all the linear combinations of the columns, and these R columns of U are enough to fully describe it, so these R columns are all you need. Okay. Now, so now let's suppose I truncate this expansion even further. So I have fewer than R terms. What does that mean? It gives me the best rank K approximation of A. I'll call it AK. So same kind of sum, we're just only taking the first K terms. And that's why it's important to keep in mind that the singular values are ordered. So the terms that I'm dropping are the ones that have a small singular values, so those are more negligible. Okay. So here we have this truncated SVD expansion. And it turns out that the error in this approximation in the 2 norm sense Because what is a 2 norm? A matrix 2 norm is the largest singular value. Well, these two matrices have the same k largest singular values. So so the largest singular value of the difference is going to be sigma k plus 1. So if this singular value is quite small, then you have a very accurate approximation. Now, there's a very good reason why we should care about this, because the application of this is data compression. Because how many numbers do you have in the entire matrix? Well, that's m times n. But if you have a truncated SVD expansion and you figure out that k terms are all you need because this error is nice and small, then the storage that you would really need is k left singular vectors, k right singular vectors, and k singular values. So the storage you would need is k times m plus n plus 1, and that could be much less than m times n. So if m and n are large, the storage savings could be huge. And in fact, the last time I taught, COS 702, which is a linear analysis course that the PhD students have to take, one assignment I gave them was I gave them a grayscale image, so you could represent that using a matrix where each entry is a pixel value from 0 to 255 for black to white. And if you take the singular value decomposition of that matrix and then you only retain a few terms, then you've saved a lot of storage space for that image, but visually you can't tell the difference hardly. And you have to choose the right cutoff point, the right value of k, but that's one way, one relatively simple way in which this kind of compression can be achieved. Okay. So any questions about this best rank k approximation? All right. Ashley, Janae, are you able to see everything? I'm sure if I had the computer turned right.
Yeah.
Okay. So what I can do now is give a simple example of an SVD and what happens when you do a truncated expansion. All right, so let's suppose our matrix is okay. Now, this has an SVD, so all the matrices involved are 3 by 3. So matrix U, so we have 3 orthonormal vectors. So we have 1 over square root of 3, 1 over square root of 3, 1 over square root of 3 for first column, and then we have minus 1 over square root of 2, 1 over square root of 2, and 0. And then we have 1 over square root of 6, 1 over square root of 6, and then minus the square root of 2/3. So all of these vectors have a unit length. They're all orthogonal. And then v also, but different columns. So we have 1 over square root of 6, square root of 2/3, 1 over square root of 6, minus 1 over root 3, 1 over root 3, minus 1 over root 3, 1 over square root of 2, 0, minus 1 over square root of 2. I should mention that when you're computing like eigenvalues and eigenvectors, and especially singular value decomposition, not something that one would ever want to do by hand. This is a contrived example to illustrate some things. We will learn numerical, iterative methods toward the end of the semester. Now, the matrix that's most interesting to us is, I'm not sure why I called it S in the notes, it ought to be sigma. So the largest singular value is roughly 42.43, and then 2.45, and then 0. And then sigma is a diagonal matrix, so all the other entries are 0. So this right here is sigma 1, sigma 2 is this center element here, and then the singular values are non-negative, they can be 0, so sigma 3 actually is 0. So in other words, this matrix is a singular matrix, because we have at least one 0 singular value. Okay, so because we have two non-zero singular values, so R, which is a rank of A, would just be 2. So what we could do is we could represent A as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose. So this is V1, V2, and V3 over here. And here we have U1, U2, and U3 here. So because the rank is 2, these first two columns span a range of A. This third column of V describes the null space of A. And actually, you can see that from a matrix. If you subtract the first and the third columns, you get 0. So you can see from a matrix, well, why that be the null space? And sure enough, this vector with the second component 0 and the first and third components negatives of each other, that describes the null space. Okay. Sorry?
Would you say that again about
The null space?
yes, please.
Okay. So notice, because when you're trying to, so any vector in a null space would be a vector where it describes how you take a linear combination of these columns to get to 0 vector. But notice this matrix, the original matrix, the first and third columns are the same. So all you have to do to take a linear combination of these columns to get 0 is take this column minus this column, and you get 0. So you can see the columns are linearly dependent. And we see this in this vector here that describes the null space of A, that any vector where the first component and the third component are negatives of one another, and the second component is 0, any vector of that form is in the null space of A. You good?
Yes, thank you.
All right. Now, let's see what how the entire matrix can be represented using just these two terms. What I'm going to do now is take a rank 1 approximation. So A1 is going to be just the largest singular value, so 42.43 roughly, times, so that's sigma 1, times U1, V1 transpose. So in other words, I'm now neglecting this second term. Now, so as a result, the error in this approximation is the 2 norm of A minus A1, but that's going to be the largest neglected singular value, so that's 2.45. But to get an idea of how accurate an approximation this is, because this retained singular value is much larger than the neglected one. So what I really should do is look at relative error. So that would be the 2 norm of A minus A1 divided by the 2 norm of A. So exact minus approximation divided by exact. So we have 2.45 on top, and then the 2 norm of A is the largest singular value. So this is 42.43, and we get roughly 6%. So it's actually like 0.0577. So so having 6% error in the matrix, and yet we've only retained one term and saved a tiny amount of storage. So this is a particularly nice example where a rank 1 approximation is good enough. But sometimes it happens where you could have a really large matrix, like thousands of rows and columns, and depending on the entries, maybe you only need to retain terms corresponding to, say, the largest 5 singular values. So instead of storing like a million numbers, maybe you only need to store like a couple thousand. So again, the storage savings can be significant. And so what's interesting is for matrices to describe, for instance, images, often just a few terms are enough because what happens is the terms you're neglecting may just include details that are too small for the naked eye to really distinguish. Okay. All right, so questions about this truncated SVD example? Yes?
If the third singular value is not equal to 0, then what is the relative error? Still 6%?
Using this measure, yes. Now, you might not want to measure the error using the 2 norm. You might choose instead to use the Frobenius norm, in which, so that would change both of these, where you're taking the sum of squares of the neglected singular values up here, and the sum of squares of, or square root of sum of squares of all the singular values down here. So it might be, you might get a somewhat different measure of the error in that case. It all depends on how the singular values are distributed. But whatever singular values down here would have to be smaller than this. So it'd still be a pretty accurate approximation.
Okay, then how to decide which measure we use?
Probably based on how the singular values are distributed. Like, for instance, do they decrease slowly to 0, or is there a steep drop off? But again, like I mentioned when talking about norms in the first place, vector norms, matrix norms, they tend to be somewhat equivalent. So it's not common to have like the error in the 2 norm sense be quite small and the error in the Frobenius norm be like unusually large. That doesn't normally happen. Okay. From a practicality standpoint, well, thing is the Frobenius norm is easier to compute because, yeah, it's a square root of sum of squares of the singular values, but it's also a square root of sum of squares of all the entries in the matrix. So there's a direct way, like a simple formula for computing that one. Okay. One of the unfortunate things about the SVD, we get a lot of useful information from it, but it's also really difficult to compute. It's just as expensive as, for instance, doing full-blown Gaussian elimination or any of the other matrix decomposition algorithms. In fact, it can be somewhat more expensive. But the information you get from it could justify that expense. But one thing to think about is how much information about the matrix do you really want? Do you really want to have all the singular values, or do you only care about the largest few or the smallest few? Because the algorithms for getting all the singular values versus selected extreme ones are totally different. And in fact, when I was back in the petroleum engineering community, I actually had to embarrass some of the top researchers at ExxonMobil because in their presentation they were talking about needing to compute the largest singular value, and they were computing all of them. And I told them, like, you don't have to compute all of them just to get the one. You're wasting a lot of time. And after I embarrassed them a few times, they got it. They stopped talking about it. Now, whether they actually fixed it or not, I don't know. But they knew to stop talking about the numerical linear algebra in my house. So, okay. Any other questions about this low rank approximation? All right. Okay, this is working. Okay. All right, so one particularly important concept that's going to be a recurring theme is that of projections. Okay, so the problem that leads to coming up with projections is this. So let's suppose we have a vector z in Rn, and you have a subspace S Rn, and what we want is we're going to find a vector W that belongs to this subspace such that the difference between Z and W belongs to the orthogonal complement of S. So in other words, this difference does not have any component that belongs to S itself. Now, in other words, we're saying that this error Z minus W is orthogonal to every single vector in S. Okay. Now, it turns out that, and I've been referring to this to error because W can be thought of as the best approximation of a vector Z in the subspace S. And what I mean by best approximation is that for any vector y in S, W minus the 2 norm of W minus Z is going to be less than or equal to Y minus Z. That is, W is going to get closer to Z in a 2 norm sense than any other vector in the subspace S. And that's why we refer to W as the best approximation. So minimizing this error is equivalent to the error being in the orthogonal complement. So we can look at it from either point of view. Okay. So the definition I'm going to make is the orthogonal projection make sure I'm not going off the edge here. All right. Onto S is an n by n matrix that I'll call P such that if I multiply this matrix P by any vector Z in all of Rn, and I get the vector W as a result, then that satisfies this property that I want, that the difference between W and Z belongs to the orthogonal complement of S. So P is a matrix that I can feed any vector in Rn to it, and it's going to give me the best approximation of that vector within the subspace S. So the important thing is the projection matrix P is associated with the subspace S. So the question is, how can I find this matrix P that's going to do the job? Okay. Now, so I want W minus Z to be orthogonal to all of S. So that would certainly mean that W minus Z is orthogonal to W itself, because W is a vector in S. So this is actually a much far weaker condition than this. But this is what I'm going to use to figure out some properties that this matrix P is going to have. Okay, so using a dot product, I have that W transpose W minus Z would have to be 0. Okay. Also, the dot product is commutative, so I can write this the other way. W minus Z transpose W is also going to be 0. But I'm going to need both directions for this. Now, W is P times Z. It's my orthogonal projection applied to Z. So if I go ahead and substitute that into these equations, then I get PZ transpose PZ minus Z is equal to 0. So I'll work on this one first. And using a property of a transpose, I get Z transpose P transpose PZ minus Z is 0. And now on the right side, I can go ahead and factor out a z. So I get p minus identity times z is 0. And now I can take this p transpose and distribute it inside. So I have z transpose p minus p transpose z is 0. And also, this has to be true for all z. So this is the case for any z in Rn. Okay. Now, suppose I do the same kind of manipulations for the dot product expressed going the other way. So I have pz minus z transpose pz is 0. Now, I can write this. So first I could factor out a z transpose to the right, to the left. And then I have p minus identity transpose pz is 0. Now I can distribute the transpose into this difference. So I have p transpose. Now identity transpose is identity, so I'll just leave that the way it is. Now I'll take this p and distribute it through here. So z transpose p minus p z is equal to 0. Okay. So these two equations hold for all z in all of Rn. What does that tell me about p? What can I say that it's equal to? Just by taking these two equations together. What? Yeah, p. So first, because of these, that p and p transpose match, what else are they equal to? Well, yeah, z is any vector whatsoever. So if this holds for, if this thing is 0 for all z, what does that say about the matrix inside? I'm sorry, what? Yes. Yeah. So the thing is, because it's true for all z in Rn, this whole matrix is 0. And therefore, this matrix too is 0. So, yeah, so P is equal to P transpose, and both of them are equal to P transpose P. But if I again use the fact that P and P transpose are equal, I can also say that P is equal to what? Using the, because P is equal to P transpose, I can in fact, P is generally not invertible. Yes, because if I can replace this P transpose with P. So P is equal to P squared. So actually, I'm running on a board. So P is symmetric and it's equal to its own square. So these are two properties that any orthogonal projection matrix has. And in fact, okay. Yeah, it's too bad I'm out of board. But this actually gives two essential properties of a projection. So, so properties of projections is first, because it's symmetric and it's equal to its own square, it's unique. So that's something that can be proven. And there actually is a nice formula for it. If the dimension of your subspace S is equal to K, and V, which is an n by k matrix, so it's n rows, k columns. So it has orthonormal columns that span S. So in other words, the columns of S form an orthonormal basis for S. Then I can say that the projection matrix is equal to V times V transpose. Now, one thing to keep in mind, if you have a matrix that has orthonormal columns, like this matrix V here, I can say that V transpose V is identity, the K by K identity. But you cannot say the same about V transpose. That is generally not identity. The only time that is identity too is if the matrix V is square. In that case, V is an orthogonal matrix. V here, if K is less than N, it is not an orthogonal matrix. It does have orthonormal columns. So we have this, but not this. So in a non-square case, we get this being a projection matrix onto the space spanned by these orthonormal columns that do not cover all of Rn, just this subspace S. I should mention that so a commonly used formula for projections in a case where you do not have an orthonormal basis. So you have a basis, it's just not an orthonormal basis. So then the formula for a projection is V, and then you have V transpose V inverse V transpose. And if V has orthonormal columns, you can see that this reduces to this because V transpose V is identity. Now this could be useful. For instance, suppose you have a matrix A, and the matrix has a range that only occupies a subspace of Rn, not the whole thing. Then if you want a projection onto the range of A, you can just form this. So it'd be A, then A transpose A inverse times A transpose, and that would give you that projection. But you can see when you have an orthonormal basis, that we have a much simpler formula for a projection. Okay. All right. So now I can do an example involving projections. To see why the projection is unique, you can have infinitely many orthonormal bases, but you only have one projection. And the reason why that is suppose I change from this orthonormal basis V to a different orthonormal basis. Well, that means the only way I can do that is I'm multiplying V on the right by an orthogonal matrix. So I'd have something like VQ times Q transpose V transpose. The Q and the Q transpose in the middle will become identity and cancel out. So that's why even though you have infinitely many orthonormal bases, you only have one projection matrix. Any change of basis would cancel out in P. If you want, you can try working it out yourself and see why that is. Okay. All right. So as an example involving projections. So I'll let my subspace S be subspace of R3, and S is a span of the first two standard basis vectors, E1 and E2, which this is known as I and J. So this is 1, 0, 0. This is 0, 1, 0. Okay, so I'll define V to be matrix whose columns are E1 and E2. So that's 1, 0, 0, 0, 1, 0. Okay, so now what I can do is form a projection onto S. So that'd be V transpose. So that's 1, 0, 0, 0, 1, 0. And then V transpose would be 1, 0, 0, 0, 1, 0. So if I go ahead and carry out this matrix multiplication, I'm going to get a 3 by 3 matrix. So it's kind of like an outer product, except now you have 2 columns instead of 1. And what you get is 1, 0, 0, 0, 1, 0, 0, 0, 0. So that is the projection matrix. And you can tell that what this matrix is going to do, if I multiply this with any vector, it's just going to take the first 2 components and zero out the third one. So if I let Z be the vector 3, minus 4, and 1, then my best approximation of this vector in its 2-dimensional space, so I'd be 0, 0, 0, 0, 0, times 3 minus 4 and 1. I'm just going to get the vector 3 minus 4 and 0. So that's my projection of this vector onto this 2-dimensional subspace. So the error is going to be this component that went from 1 to 0, but that is the best I can do. There's no other vector that's contained within this 2-dimensional subspace that could possibly get closer to this one, which you can confirm for yourself visually in this low-dimensional case. Now, the concept of projection is quite important throughout numerical analysis, not just when you're dealing with vectors in Rn. In small, low-dimensional spaces like this, it's important for visualization, like you're taking 3-dimensional vectors and projecting them onto 2-dimensional space for viewing, but also for vector spaces where the vectors involved are functions. So for example, operations such as the Fourier transform, they perform projections. So your vector Z would be, for instance, a vector of function values at various points. So the operation of taking the Fourier transform can be used to project that function onto a relatively low-dimensional space consisting of like sines and cosines of limited frequency. So any kind of operation of approximating a function by functions of a certain type. So you are performing polynomial approximation or approximation using sines and cosines, like in the Fourier case. All of those, or not all of them, many of these operations involve some sort of orthogonal projection, because you're trying to make that error, in some sense, as small as possible. Okay. Oh, okay. I know I had some good topics lined up for finishing off in the last 23 minutes. Okay. Any questions about this example? wrap up this chapter that has so many matrix analysis preliminaries, and we'll be segueing into solving systems of linear equations. And a very important concept for that is, if you have a system of linear equations, ax equals b, how sensitive is the solution to changes in a and b? Now, let's suppose that A is invertible, or non-singular. Then I can express, so it turns out I can express the inverse of A using the SVD. So if A is U sigma V transpose, then if A is invertible, all these matrices in the SVD are invertible. So A inverse is going to be V transpose inverse, but that's just V, sigma inverse, then U transpose. So that's the SVD of V inverse. So if I have a system of equations, AX equals B, then as the solution, X is A inverse B. But now if I express that in terms of the SVD using outer products, I'm going to have VI UI transpose. And now, because I have the inverse here, I'm dividing by singular values that are all non-zero in this case because A is invertible. So, I'm multiplying this by B, so I have B here. So here I have a dot product of each left singular vector with B multiplied by the vector VI. So the solution is a linear combination of right singular vectors. Now, okay. So let's suppose that sigma n is small. Sigma n is a small singular value. It has to be positive in this case, but it could be really tiny. Then, because it's small, what could happen if I make a small change in the right-hand side vector b? Well, what could happen is small changes in b could be amplified in the solution X. So you might think, oh, I'm making a tiny change in A or a tiny change in B. The solution X is not going to be thrown off by very much. Well, that could happen, but not necessarily. You can't be sure, because depending on the properties of A, like how close it is to a matrix that is singular, a tiny change in A could really throw off, or a tiny change in B could really throw off X. In fact, I can easily contrive an example where you make a change in B of like on the order of 10 to the minus 8, and the change in solution is on the order of 10 to the plus 8. It can be done. Actually, I have an example in the notes. So I'm going to use norms to do a quick analysis of what happens if A or B change, and to what extent could that throw off a solution. So the idea is we let A and B be perturbed by a small amount, and then we see what the corresponding changes in x. Okay. So our perturbed system so we have A plus epsilon E. So E is some matrix that's used to represent a change in A. And then because the system is changing, the solution is changing. So we'll make a solution, x, a function of epsilon. And the right-hand side will be perturbed as well. So epsilon is used to account for both changes. Okay. Now, if I perform a Taylor expansion of a solution just to a couple terms, I can say that x of epsilon equals x of 0 plus epsilon times x prime of 0, and then additional terms, which I'll neglect, because those are of order epsilon squared. The idea is epsilon is small, so this would be far smaller. So this derivative, x prime of 0, is a useful measure of the sensitivity of the system. So if that's large, we can have a large change in x, even due to a small change. Okay, so what I'll do is, if I go ahead and rewrite this, okay. So x of epsilon is okay. Well, let's see. I don't want to do that yet. What I'm going to do is, well, I'm still going to use this. I'm going to differentiate both sides. So for that, I need to use the product rule. So I'm going to have a plus epsilon e times the derivative of this, x prime of epsilon. And then the other half of product rule will be e. I'm differentiating with respect to epsilon. And on the right side, I'm just going to have e. Okay. Now, I'll plug in epsilon equals 0.
Dr. Lee,
Yes.
in the line under the Taylor expansion, that's not a prime on that x. The next under sensitivity, right?
Here?
Yes.
Yes, that is a prime.
All right. Okay. And then we're ignoring all of the other.
Right. Yeah, but like the higher order derivative terms, we're ignoring those.
Right.
Oh,
Okay.
okay. So after I carry my differentiation here, I set epsilon equals 0. So now I have a x prime of 0, which is what I want, plus e x. So plain x by itself, that's x of 0, is equal to little e. So now I can rearrange and solve for x prime of 0. So that's going to be a inverse times little e minus big E times x. Okay, so now I at least have an expression for the derivative. Okay, now, okay. Yeah, I'll need to go to the board. Okay. Now, if I take norms, I have x of epsilon minus x, and I'm just taking some vector norm of it. I'm also going to divide by the norm of x because I want a relative error. So that's going to be equal to epsilon, absolute value of epsilon, times the norm of x prime of 0 over the norm of x plus additional terms of order epsilon squared, which again I'm neglecting. So now I can fill in my expression for x prime of 0. So that is A inverse little e minus epsilon x all over the norm of x. Okay, I'm going to not write order epsilon squared all the time. So this is an approximation. Okay. Well, actually, yeah, I do need to leave it in there. Okay. Now, at this point, I can use properties of norms. The norm of a product is less than or equal to the product of the norms. So I can say this is less than or equal to epsilon times norm of A inverse, norm of E, and then here I'm using a triangle inequality plus norm of A inverse times the norm of big E times the norm of x all over the norm of x plus order epsilon squared terms. Okay. Now, so what I'm going to do is, okay, I'll break these two up. So I have norm of A inverse, norm of E over norm of x. And in this first fraction, I'm going to multiply and divide by the norm of A. You'll see why momentarily. And over here I have norm of A inverse times the norm of E. Okay. All right. And actually I'm going to multiply and divide that by the norm of A as well. In the second fraction, the norms of x cancel out. Okay. Now, what I can do in this first fraction, notice I have norm of A times norm of x. Well, so off to the side here, I have norm of B is equal to the norm of, B is equal to AX. So that is less than or equal to the norm of A times the norm of x. So what that means is, if I take 1 over both sides, 1 over the norm of A times the norm of x is less than or equal to 1 over the norm of B. So I can make this larger by replacing these two norms with norm of B. So now what I get is this is less than or equal to epsilon, and I have norm of A inverse, norm of A inverse, norm of E over the norm of B plus norm of A inverse times the norm of big E divided by the norm of A. Now, norm of little e over the norm of B, that is the relative change in B, because aside from the factor of epsilon. Norm of big E over norm of A, that times epsilon is a relative change in A. So, for relative change in the right-hand side vector and the matrix is amplified by this factor here. In both cases, norm of A times norm of A inverse. So that gives you an idea of how much a change in either aspect of a system can be amplified in a change in the solution. So we need to focus on that number. Okay. People in Skype, were able to see everything on this board?
Yeah.
Okay. All right, so a definition I'll make is kappa of A. I know this is a slanted K, but whatever. The norm of A times the norm of A inverse. And that is called the condition number of A. Now, it can be, the condition number can be measured using any matrix norm. So the condition number in like the 2 norm is going to be different from a condition number in the Frobenius norm. So what we see in this analysis here is we want the condition number to be as small as possible. So large condition number is bad. So when it's large, we actually say the system of equations is ill-conditioned. So it's always greater than or equal to 1. So 1 is what you would prefer. In fact, if A is an orthogonal matrix, the condition number is 1 and is perfectly conditioned. There is a nice formula for the condition number in the 2 norm. That is the largest singular value divided by the smallest singular value. So if the singular values vary widely in magnitude, then you have an ill-conditioned matrix. So it's not just a matter of whether this is small or this is large, it's how large sigma 1 is relative to sigma n. So you could have sigma n be kind of large, like maybe 1 or something, so definitely not negligible, but if sigma 1 is out of this world, then you still have a problem. Okay. All right. Now, let's see. Oh, 6 minutes. Okay. Now, so actually, yeah, I have an example to notes of just a 2x2 case where I show that so like an example of a matrix that is well conditioned and a matrix is ill conditioned. One of the unfortunate things is it's very difficult to tell if a matrix is going to be well conditioned or ill conditioned just by looking at its entries. So you actually have to try to compute the norm of A, and norm of A inverse can be difficult to compute, but maybe you can try estimating it. In fact, there are techniques out there for estimating the condition number of a matrix as quickly as possible, because this quantity here, or this, are not ones that can generally be computed quickly. Okay. Now, so I want to talk about how can you tell if a matrix is either singular or nearly singular. Because you have to be careful about which measure you use. Okay, so if we first focus on the question of when is a matrix an n by n matrix A singular? Now, there are lots of ways to tell, but what's one of the most straightforward ways of classifying a matrix as singular? Determinant. All right, so that's one, the determinant of A is 0. Now, another way is if the smallest singular value of A is 0. But now if we focus on a slightly different question, when is A nearly singular? So you might think, oh, well, if either of these being equal to 0 says it's singular, then either one of these being close to 0, so quite small, indicates it's nearly singular. Well, it turns out that if you think you want to use this, that is wrong. It's this measure the smallest singular value of A being nearly 0, that is much more reliable. In fact, you can say that sigma n is the distance from A to the nearest singular matrix. And by distance, I mean I'm measuring distance in the matrix 2 norm sense. So let's suppose that the small singular value of A is, say, 0.01. Then you could say that what that means is you could take your matrix A and perturb it by a matrix whose norm is 0.01 and get a matrix that's singular. So a change in the entries by that much could actually give you a singular matrix. Now the thing is, you're doing an n by n matrix and you're perturbing entries. You could perturb them in n squared directions or n squared directions. So you don't know which direction will take you. But the thing is, if this tells you you're near a singular matrix, that means you're going to have difficulties when trying to solve system of equations involving that matrix. So the determinant can give you a false indication. For instance, you can have a matrix whose determinant is really negligibly small, but it's nowhere near a singular matrix. On the other hand, a matrix like this that is upper triangular, so it has ones all the way down the diagonal, zeros in the lower triangle, and then I'm going to put a big -1 here to mean that all the entries above the diagonal are equal to -1. So it turns out that the determinant of A is upper triangular, so you just multiply all the diagonal entries, so the determinant is 1. However, and in this example, I'll make this a 10 by 10 case. So the small singular value, sigma 10, is roughly 0.003. So it's actually really dangerously close to a singular matrix, even though the determinant is not negligibly small. And in fact, the condition number in the 2 norm of A is nearly 2,000. So this is not definitely not a well-conditioned matrix. So in fact, what I can do is I could make a slight change to A where the entries only change by you don't even notice a change in the 2 decimal places, and the matrix actually is singular. So this is one reason why the determinant is not really used very much for the numerical linear algebra as opposed to theoretical linear algebra. It's just not practical. It doesn't give us the information we need about how sensitive a system is to round-off error and things like that. Okay, oh, I'm over time, but that's the end of chapter 2, so we get to chapter 3 on Wednesday. There's no class Monday because of the Mardi Gras break.
Bye.
Yes, bye.